options in college. You could do a 2-day a week or a 3-day a week. And then like, I don't know, they just transitioned to more of a 2-day a week thing. I don't know why, but
I just feel like for a class like this one, you'd be getting a little bit of extra time every week or two. Just so much less exhausted by the end of the class. Because by the time I'm out of here, I'm like drained in.
I thought that this was invigorating. No?
I mean, don't get me wrong.
You don't leave here like skipping out of the room?
You leave recharged.
That's the way you feel? All right. Okay, let's get started because like I said last time, we have a lot of stuff to do, right?
Let's do it.
We ready? So I sent an email out this morning about the R3 and how we have the right-hand rule. And so it's hard when you're looking at it to know what's what. So I've color-coded everything. And that's why I reissued the notes. Y'all get all those emails? All the interactive notes have been reposted. If you want to download them, you can. Yeah. And I sent an email this morning explaining that from here on out, here's our R3. From here on out, the x-axis is red, right? Right-hand rule. X-axis positive, red, curls to green. Thumb is in the blue, right? So positive x curls to positive y up this way. Got it?
X, Y, Z. Gotcha.
X, Y, Z. Now look at this picture right here. Is this correct? Is this in the correct right-hand rule orientation? Look at this picture. Look at this right here. Is that what that is?
Yeah. Probably. Just
Yes.
190
Yeah, I mean, you just have to like, maybe look at it this way. So remember that when you're looking at these images, you know, you can be looking from all sorts of directions, right? The most important thing is that we know that it's that we're following the right-hand rule, all right? Okay. Put that over there. So I guess what I'm getting at is if I turn, where is it? Did I open the wrong one? I opened the wrong one.
The ones with the axis labeled on the positive into the axis, right?
Yes, the ones that are labeled X, Y, Z, that's the positive direction. So that right there is what we're looking at right here, like this. Okay, so I redid this. The red, the green are the positives. Okay, of course the red goes that way as well, but I wanted to leave that axis not colored so that you would know where the positive axes were. Make sense? Okay. All right, that's first thing. Now, I wanted to talk about our schedule real quick.
All right.
Because this is Cal 3, right? The calculus actually does not begin until chapter 11. So I just want to kind of like, if you're sitting here going, well, you know, I've seen vectors before, I just wanted to kind of recap, like we are doing first, it's like an introduction to three-dimensional space, 3D coordinate system. We're talking about vectors, dot product, cross product. Then lines and planes is usually new, and that's going to be a kind of challenging section. Quadratic surfaces is usually new, but none of this requires a derivative or an integral or anything like that. Everything is just definitions and understanding what's going on and visualizing, all right? And then once we've got all that framework in place, then we start doing the calculus. And it'll be just like it was, like chapter 11 is basically Cal 1, but in higher dimensional space. So you have the idea of a derivative, tangents, chain rule, max and mins, right? Max and mins, that's all Cal 1 stuff. Then you get to chapter 12, now you're doing integration, integrals, right? Double integrals, triple integrals. And then you get to chapter 13, and that's where you start to bring in vector functions, which is going to be new to most of us. So, I mean, well, all of this is going to be new, but we've never done any sort of things with integration involving vectors. So that's what chapter 13 is about. All right? I just want to I didn't do that on the first day, so I want to just kind of lay it out to you. If this seems like, you know, Cal 3 is going to be pretty easy. Vectors, it's easy. Like, just wait, the calculus is coming. It's not that it's going to be harder, but it's coming, all right?
The fun part's not.
The fun part's coming. We're just laying out framework
we
at this
don't
point.
get to the fun part till after exam 1. Sorry.
All right. Notes. Where the heck are they? Where are my
I think that's
notes?
still your PDF.
Yeah, I know, but it should be right here. There we go. Okay, so last class, what we had done is we had established how it is that you define a vector, or what the notation was for a vector if you're given 2 points, right? So if you have 2 points on a flat sheet of paper, right? So if we're in two-dimensional space, if you're given 2 points, I gave you the definitions on how to write those vectors in using the angled brackets, right? So now what we're going to do is we're going to talk about what's the notation for doing a vector. What's the notation for a vector in three-dimensional space? So if you're given 2 points, right, in three-dimensional space, how do you define the vector that goes from one point to the other? And there's good news. It's the exact same formula as it was for two-dimensional space, except that you now have a z to worry about. So this definition says, let A be some point x1, y1, z1. So you have an ordered triple, right, x, y, z. And then you have another point, and given the x, y, z, then there are 2 ways you can define a vector. One that goes from A to B, or one that goes from B to A. And so these are here. I'm not going to write them. We're just going to get to an example. So let's do this one right here. And I'm only going to do one of these because I think it's intuitive to get the other one. So let's do part B. Let's do the vector that goes from B to A, right? So to do this, what I'm going to do is start by subtracting the x-coordinates, right? I'm going to do an angled bracket. I'm going to start by subtracting the x-coordinates. Which one goes first, though? I'm going from B to A, right? So you start by taking the x-coordinate on A or B? We're going to where? We're going to A, so that's the one you start with. All right, it's a little backwards. So I'm going to start with the 6 here and subtract from that the x-coordinate of B. So I'm going from B to A, right? This is the point 6, negative 5, 6. And then this is the point negative 2, 8, 10. So I'm going from here to here. So I will start by taking that x-coordinate, subtracting that x-coordinate, comma. Then I take this y-coordinate and subtract that y-coordinate. So negative 5, take away 8. Sorry about this. I'm in my own way here. And then last one, 6 take away 10, right? And that's just arithmetic, right? So we get, what do we get? The vector 8,
negative 13, and
negative 13, and negative 4, right there. That is the vector in three-dimensional space. That's your vector that connects those 2 points. So if we were to go here, and figure out where A is and figure out where B is, right? And then connect them with the vector from B to A, we would have this vector sitting in space like this, right? And that is the way we write the vector using the angle brackets. Now, I know some of you are linear algebra. I asked, right? How many are linear algebra? 1, 2, 3. Right now you're in linear algebra? So in linear algebra, when you deal with vectors, this is, where's my eraser? This is a vector, right? But in linear algebra, depending on the book and depending on the instructor, you might use a different notation, which is to write it like this: 8, negative 13, negative 4. And that's called a column vector. And it's the same exact thing, it's just a different sort of notation, all right? So sometimes you'll see this, and sometimes you'll see this. Our textbook uses this notation exclusively. But I want you to understand it could be that. And that's useful in linear algebra when you're dealing with matrices. It's easier to look at things this way. So just be aware. All right, any questions on finding a vector from one point to the other? The order matters, yes?
A to B, just the signs are...
A to B is just the reverse. So basically you're going to have a negative 8, positive 13, positive 4. All right, now we define a new vector. We talked about it when we first talked about the definition of what a vector is. And I said that there's one exception, because the definition of a vector is any object that has some sort of length, magnitude, and some sort of direction. And that's the definition as long as you're not talking about these vectors. So in two-dimensional space, we have the vector 0, 0. And we denote it with a bold 0. You have to have this little half arrow on top, okay? Because there is a huge difference between writing this and writing this. This is the number 0. This is the vector 0, the 0 vector, which is actually this, okay? So that's like a cat and that's like a dog, right? They're totally different things. And in 3-dimensional space, your 0 vector would be 0, 0, 0, and then in 4-dimensional space, 0, 0, 0, 0, right? And so on and so forth. What do you think the 0 vector looks like in 1-dimensional space?
0?
Okay, so is it this?
No.
You would have to write it with the angle bracket. So in R1, the 0 vector would be that vector. All right, can I continue? It's just a definition. Yes?
Do you have to write the brackets like these, or can it look a little more like a straight line?
Oh, yeah, sorry.
No,
No, it is an angled straight, like it is a sharp corner there. That's just me going fast.
but it's supposed to look like.
Yes.
Okay.
It's on your on like a keyboard. It's above. Where is it on here? It's above the comma and the period on a keyboard. It's an angle bracket.
They're like that because of vectors, right?
Well, that's the notation we use for them.
Yeah, but we use that for vectors, right?
For vectors, yes. I mean, you can use it for other things as well. Just depends on. I mean, we run out of symbols in math, like so. Sometimes we use the same symbol for different things, but normally it's a vector. All right, so some language here. I'm unmuted. I'm recording. Let me just do something real quick. Yeah, it's working. All right. So some language. If we have a vector in 2-dimensional space, then it's going to have a number here and a number here, right, with the angle brackets. The first number is called the x component of the vector, not coordinate, okay, not coordinate. We save the word coordinates when you're talking about a point. Like let's say I have that point 4, 5. That's a point on a flat sheet of paper, right? That is not the same as a vector because a vector can be moved around, up, down, left, right, yes? As long as you don't change the length and direction. So we have different terminology. This first number is the x component, y component. If you're in 3-dimensional space, then you're going to have 3 numbers. The first is the x component, second's y component, and then the third would be your z component. Clear? All right, geometrically, we are going to talk about adding vectors now. So let me back up because there's kind of a big picture that I want you to be thinking about right now. We have this idea of a vector, right? And well, I'll call it V. Let's say we have this vector V. So think about when you're in grade school and you're learning like numbers, right? You learn, hey, 4 and 7. You learn about numbers and then what do you learn to do with them? Add them, then subtract, and then multiply and divide, right? So now we have these new things. They're not numbers, they're something else. They're called vectors. And so what we're going to want to do with these vectors is learn how to add them, subtract them, multiply, and divide, right? We want to be able to do some operations on them. Now, what it's going to turn out to be is that addition is going to be easy, right? Subtraction is going to be easy. When it comes to multiplication, with numbers, it's pretty straightforward, right? 4 times 5. Like we only have one type of multiplication with numbers, right? There's only one kind. With vectors, there's 3. There's 3 types of multiplication. There's scalar multiplication, there's the dot product, and there's the cross product. So we have to make sure we understand how to do them, what they represent, right? And then we'll implement these things later on. So I'm just trying to give you like a step back. That's what we're about to do. Talk about vectors, how to add them, subtract them, then we'll get to the 3 multiplications. And then as far as division, there's not an easy way to, well, let's just get to it. I don't want to get too far ahead of ourselves here. All right, so how do we add vectors? Okay, how do we add vectors? We're going to look at it first geometrically, and then after we do it geometrically, we're going to look at it mechanically, like if we're given the vectors, how do you add them? And the good thing is, like I said, this is pretty straightforward in terms of how you do it mechanically. Visually, when you add 2 vectors together, It doesn't matter if you're in R2, R3, R4, Rn. Doesn't matter what dimension you're in. The way you do it is you take one vector. Where's my other vector? Here we go. So if you want to add two vectors together, imagine that these have arrows on them, right? Let me put my arrow on here. There's my arrow there. Nobody uses these to measure anything. See my arrows? Okay, so this is my, what do we call that point right there? Tail. We call that point up there terminal point, or tip, tail, right? Tip, tail. So you've got these two vectors, right, living in three-dimensional space. Because they're vectors, I can move them up, down, left, right, doesn't matter, right? I just can't change the direction, can't change the length. So to add these two vectors together, what you're going to do is you're going to just leave one alone. You're going to take this one, slide it over, move it, and you're going to attach the tip of this to the tail of this one, okay? So you see them there now? They're like this, sitting in space. You took this vector, you added this vector. The answer, like what you get when you add two vectors together, is a new vector, right? So what is that vector? It's the vector that goes from this tail to that tip. So can you imagine a vector that connects here to there?
Yeah.
You all see it? That's the sum of these two vectors. So I have that visually here. Here's two vectors. I'm just going to pick one of them. I'm going to slide it around. Let me see. Let me move it this way. Let me move it up. See, I'm about to attach the tip of the red one to the tail of the blue one, right? And when I do that, I get the answer, which is the vector connecting the tail here to the tip of that one. So it's almost like you're traveling somewhere, like you're going, let's say, from Austin to San Antonio and then back up to, I don't know, what's west of Austin? Bernie-ish area? No, who cares? You're going from here, down here, here, right? The result is that you wound up going basically from here to here, right? We call this vector the resultant vector. It's tip to tail, tail to tip. See it? Yeah? Questions? Yep. Okay. Now what I'm going to do is I'm going to draw that so it stays there. I'm going to draw that blue one again. There's that blue one. I'm about to move it. I didn't bring my purple with me. Oh well, I'll do green. So this was the result, right? This one right here was v plus u. That was the sum of those two vectors. All right, now, I could have moved either one, right? I could have moved either one. As long as I go tip to tail, you should get the same answer. So this time I'm going to move that blue one down, move it this way, and move it back up, right there. Okay, you see that? I attach this time, here's the u. I attach the tip of that to the tail of v. Right, so the result is that I went up and then down, but that's really like going from here to here. Do you see that these two are the same? Mm-hmm. Same vectors? They're not in the same position, but vectors, it doesn't matter where they are, right? So, but it gives you the same answer, doesn't it? So again, this is called the resultant vector. So the main takeaway from this is that when you're adding two vectors, whether you're in two-dimensional space or three, it's always tip to tail, or you can say tail to tip, doesn't matter how you say it. It doesn't matter which one you leave alone, which one you move. You can move them both as long as you go tip to tail, tail to tip. Yes?
Does it matter if you leave it as v plus u or if you just write vector v?
I should have, I like the notation like this better. V plus u. I like that better, actually. Is that what you're asking? Yeah. All right. Now, that example right there is in two-dimensional space, but can you imagine that in three-dimensional space as well?
Yes.
Okay. Yes? Was that a question? Yes. Oh, you got purple. Thank you. Maybe I might need that. All right. So this next one, I think I'm only going to do one of these. What I do is I give you three vectors, v, u, and w, and I ask you to just use these pictures to do v plus u, then u plus w, and then add all three together. So which one should we do? A, B, or C? What do you want to do? You want to do the one that has the most involved? Okay, so let's do v. I'm going to add u and add w. So here's v. I'm not going to move it, right? And so what I'm going to do next is I'm going to add to it u. So I'm going to take this blue vector right here. All right, there's my little blue vector. And I'm going to attach the tail of this one to the tip of this one. And make sure I don't change the angle and change the length. So I'm going to move it over, I'll move it down. I don't know. We're going to kind of eyeball this. What do y'all think?
It's up 2 across 1.
Yeah. But just basically like that. Y'all happy with that?
Yeah.
It's not very parallel, but yeah, we good enough? Okay, and then I'm going to add to that W, which is this red one. So I move that one up and that one over like that. So I get something like, try and do a little better on this one. Any better? So that's W. And then this was U. There's V. So what is the answer?
You have to connect
I have to connect what?
from the
Tail of
Tail of V to the
tail of V to the tip of W, right there. That vector right there is V plus U plus W. And it turns out that if you would have done it in any other order, like left the W there, then added the U, then added the V, you would eventually get to the same exact vector you're looking at there. We good?
So,
Yep.
no. It was an observation that I think is actually pretty worthless. So.
Okay. All right. I'll trust you on that. All right. The next thing, that's how you add vectors visually. All right. That's the visual sum of two vectors. Now, to do it mechanically, like if someone actually gives you the vector v1, right? v1, v2, u1, u2. So this is a two-dimensional vector. This is a two-dimensional vector. To add those two vectors, very simple. You just add the components together, right? I just take the x component of this one and the x component of that one, add them together. Add the y components, boom, that's it. We get an answer that's a vector. Same with subtraction, sorry. If you do subtraction, same thing. But with subtraction, does order matter when we subtract things in the real world? Like not in the, with the numbers, does the order matter? Absolutely, right? So when you come to subtract vectors, if you do u minus v, you have to do it in that order. You have to do the u, the x component of u, subtract the x component of v, and then you do the y component of u minus the y component of v. And then all of this extends in a three-dimensional space. You just have the additional third component to worry about. Am I going too fast, or is this okay? You all right with this? I mean, it's just definitions. Again, don't sit here and copy all this down because it's in your notes. May I proceed? All right, our first type of multiplication. All right, our first type of multiplication, remember I said there's three. First one is called scalar multiplication of a vector.
Yep.
So scalar multiplication means you start with a vector v and a scalar c. What do I mean by scalar? What's implied with that?
As a line that isn't a vector, doesn't have direction.
It's a what? You said a line. Did you say a line?
Yes, I believe it would be a line without any direction.
No.
It's a value.
It's a value.
That wouldn't have any effect on the actual
Oh, is
system.
it just
So it's just a number.
It's a number that can scale things up or down and doesn't actually have any effect on the bearing of the system because it doesn't actually affect the system.
Well, it'll impact the vector. It'll have an impact. What I'm asking is, what is a scalar? Like when I say scalar in this class, what am I talking about? You're talking about what scaling is. To scale something means to change the length, right? I'm saying what is a scalar? It's a constant. It's a number. That's it, okay? That's it. That's all. I want you to make sure everyone understands. When we say in this class, you have a scalar c, c is just a number. It's not a vector, it's a number, right? So to start this out, if we want to define this thing called scalar multiplication, it just means we're multiplying a vector times a number. That's all it means, right? So we're taking a vector and we're scaling it. We're multiplying it by a number. So the way we write that is c times v. And all that c does is changes the length of the vector v. It scales it. Either it makes it longer or it makes it shorter, or if it's a negative number, it's going to flip it over. So let me show you first how you actually write it out. If you're given a vector, v1, v2, multiply times the number, scalar, then all you're going to do is multiply each component by that scalar. So if this were a 2 here, you would just double each of the components. If this was a -3, you'd multiply each component by -3. That's the way scalar multiplication works. Very straightforward. It's almost like a distribution. Visually, this is what happens. So what you see in front of you here is me scaling a vector. So here's a vector v, and what I'm doing is I'm multiplying it times 2.75, and what it does is it stretches it out, makes it longer. It's 2.7 times longer than it was. And then I can, let me see, should we leave the vector there? We'll leave it there. If I multiply it by a bigger number, it's going to go off the page, but if we come back, let's see, if I multiply times 1, it's the same vector, right? Because you haven't changed anything. If I multiply by a fraction like 1/2, it's going to shrink it, right? Something like that. It'll be half as long. Yes?
Are all unit vectors just scalar vectors?
Are all unit vectors?
Are all vectors that we perceive just scalar vectors a unit vector?
Yes. All vectors are, well, not, it's a little more, it's almost that. It's almost that.
You're right.
It's a linear combination of 2 vectors, which we're actually going to do that in just a moment when we get to I hat, j hat. So here I'm multiplying by a positive number. It's either making it bigger, right, or it's shrinking it. What if I multiply by the scalar 0? So what if I take some vector v and multiply it times 0? I will get the what? 0 vector, right? This would give me the 0 vector, which would basically be, it's not really a vector anymore, right? We said the 0 vector is that one exception. Doesn't have a length, doesn't have a direction. What it would look like for us is basically like a point at the origin, but you can move that point around anywhere you want. See, it's undefined here?
Ooh, beast.
Yeah, okay, so it's undefined because of my code. Yes?
So I have a question, because the nature of the components is actually throwing me off a little bit.
Okay.
Because we're only getting a single point from the component. Is that effectively, is the assumption given of components that our tail is at 0?
Yes.
Okay.
Yes.
So we assume
Well,
0, 0, and then we come.
If you want to draw it, okay, so here's the question. It's a good question, all right? So let's say you're given the vector, let's stick with 2-dimensional because it'll be a little easier. Let's say you're given the vector 2, 3, and I ask you, hey, draw that vector, right?
Yeah.
The best way to draw this vector is to treat it almost like this is a point in 2-dimensional space. Go out 2, go up 3, right? There's the point. But then draw a vector that goes from the origin to that point. Now that is the vector, let's call it u, okay? That is the vector u. Now you're free to move it around.
Yes.
Okay.
Yeah, but I knew that, so I was just trying to work out, if I'm giving these 2 points, how do I know?
If you're given these 2 points.
Yeah, because if you look at it, not 2 points, the coordinates.
Components.
The component, yeah, because it does look, it is effectively just a set of coordinates, but they're being used for a vector, so it's a component. So I was just trying to figure out how to draw it, that's all.
That's it.
I understand.
That's it.
That's all.
Yeah, then you could translate it around wherever you want. Okay, so as far as the scalar multiplication, like these notes said, it all says it here. If the absolute value of c is bigger than 1, it stretches it. If the absolute value of c is between 0 and 1, it shrinks it. And if the c is a negative number, it will flip it over and then either shrink or stretch. Do I need to show more? This all extends into 3-dimensional space as well, right? If we're not on a flat sheet of paper, same thing. It'll either stretch it, shrink it, or flip it over. All right, parallel vectors. This is kind of weird, all right, because, well, let's look at the definition. Any two non-zero vectors are said to be parallel if they are scalar multiples of one another. That's all it takes to be parallel when you talk about vectors. So where's my... Here are my vectors. Did I wipe the tip of this off already? I think I accidentally wiped the tip off. So let's say that this is the tip. Okay, this is the tip. They're pointed there like that. Okay, do those look parallel to you? They look like they pointed in the same direction? Well, if I moved it like that, yes, you'd see it, right? So it doesn't matter where they are. These would be parallel. Now, what this is saying is that you can change the length of this vector, and they're still parallel, okay? You can even flip this over and have it point in the other direction, and they're still parallel. Because this is a scalar multiple of this. It is this vector multiplied by some negative number, and then shrunk or stretched. So the direction does not matter when you talk about parallel. All that matters is the scalar multiple part.
What about location?
Location never matters for vectors. Just as long as they're pointing in the same direction, doesn't matter what their lengths are, as long as they're some multiple of one another. So like if someone gave me two vectors, if I wanted to know if they were parallel, right, let me give you a simple example. Let's say we have this vector in three-dimensional space, 1, 2, 3. Somebody give me a vector that's parallel to this. What? 2, 4, what? 6. 2, 4, 6 would work. I heard you. Hold on. 2, 4, 6. Why are these two vectors parallel?
Because it was multiplied by 2.
Because you took this one and multiplied by 2 and got that one, right? All right. How about this one? How about negative 1/3, negative 2/3, negative 1? Are these two parallel? Yes. Why?
Divided by negative.
You took this and divided everything by negative 3. So you scaled it, right? To get from here to here, you scaled it by a number. It doesn't matter if it's a positive or negative number. All three of these vectors would be parallel to one another. If I change that to a +1, are these parallel? No. Because they would have to be a single number that multiplies through to get each, the components would have to match after scaling by one number and one number only. All right, next thing. The magnitude or length of a vector. So we want to be able to, given a vector, right, given the components of a vector, we want to be able to figure out how long it is, right? If somebody gives us the actual like angled bracket version. So in two-dimensional space, to find the length of the vector, we use the absolute value bars around the vector. And all you do is you take the square root of the sum of the components squared. So you just square each component, add them, take the square root. And that should make sense. It's like a Pythagorean. Think about your vector. And what you're doing is you're taking the v1, v2. That's your two sides. A squared plus b squared is c squared. And then you take the square root to solve for c. Does that kind of make sense where that formula comes from? Mm-hmm. OK. And then in R3, if you have a three-dimensional vector, it's the same sort of story. There's a notation. And you just have to add the v3 squared, which goes back to that distance formula from last class in three-dimensional space. Remember when I drew that imaginary triangle in here? OK.
Are a lot of base functions inside of calculus 3 based off of that magnitude? Is it the unit circle or the...
Are a lot of what?